Good afternoon, everyone. Welcome. My name is Tony Haymet. It's my great pleasure to welcome you here. I want to start off by thanking Hub Culture for the opportunity to use this wonderful room and to talk to you this afternoon. And on the first slide, I want to thank the U.S. taxpayers who, for 52 years, have funded through the various U.S. government agencies all of our work in climate change. So you see in the blue curve, the Keeling curve, the sort of definitive measurements, the first measurements that Dave started, that Charles David Keeling started in 1958. Although the agency has changed many times in that 52 years, it's all been funded by the United States government. What you're going to hear about today is some science and engineering that really makes it a lot easier for us to address these difficult issues. So we're going to have two parts here. We're going to talk first about ocean acidification, the measurements behind it, some of which are on the screen, the red curve, also started by Scripps, unfortunately not 52 years ago, but 22 years ago. And then we'll have Professor Andrew Dickson and Professor Vicky Fabry, who will speak about first the chemical and then biological aspects of ocean acidification. We'll break for a few questions, and then we'll move on to Professor Ray Weiss, who will talk about a top-down method for verifying exactly how many greenhouse gases that the planet is emitting. So without further ado, let me introduce Professor of Chemical Oceanography, Andrew Dickson.
Thank you. One thing I wanted to point out, you see here the red curve coming down. It's the change in the pH of the ocean. So what is pH? pH was invented here in Copenhagen 100 years ago. It's essentially a measure of the acidity, typically of an aqueous solution, a solution with water in it. And when we're looking at seawater changes, we look at changes, seemingly small changes in pH are actually very significant. And that has significant effects, as you'll see, for various organisms in seawater. Through the 1990s, there was a large international survey carefully measuring the properties of the oceans, the carbon dioxide, the water flow around the oceans, the amount of heat contained in the oceans. And this is one way of looking at it, where you can see the input of carbon dioxide. Essentially, the air contains carbon dioxide, and so it absorbs in from the surface of the ocean. And thus, at the surface of the ocean, the levels are highest, but you can see it gradually moving down. So parts of it are apparent at depths of about 1 kilometer, and in the northern Atlantic, where colder water sinks down, it goes even deeper. Now, one of the things you'll also hear about with CO2 is another part, the saturation state of calcium carbonate. This is an indication that a lot of the interest for changes in CO2 is related to how easy it is for an organism to form calcium carbonate as part of its skeleton. And so what's happening is, through time, the saturation state of calcium carbonate is changing. Here's a map showing the saturation state for one of the forms of calcium carbonate, aragonite. It's important because aragonite is corals and many, many other organisms. What you see from this picture is the location of corals in tropical and subtropical waters are all in high saturation states, the blues and the purples. This is what it looked like approximately before the Industrial Revolution. As we add CO2 to seawater, to today, actually last year, you see this decreasing. The saturation state is decreasing all around the oceans, but here you can see it most clearly in some ways looking at the areas where the black dots are, that is where coral reefs are found. As we go through this century, were we to rise to this level, 560, this is following along one of the IPCC scenarios, often referred to as a business as usual scenario. It's decreasing still further, and by the end of this century, we could be with no changes in the way we deal with CO2 at this level. Now you see that most of the oceans are unsuitable for growing corals. It's not that the coral can't grow, it's just that it has to put so much more energy into growing that it doesn't have the energy to deal with the rest of its life. So this is really one of the concerns, that this adding CO2 to the oceans changes the chemistry throughout the world's oceans. And my colleague Victoria Fabry, a professor of biological oceanography, will tell you a little more about the implications for organisms.
Well, Andrew just told you about the corals, and this is the coral belt right here. But that's not the only area in the ocean that's being affected, because ocean acidification is really a global problem. And I'd like you to focus on all the red in the high latitudes, the polar seas of both the northern and the southern hemisphere. And they're naturally low in carbonate ion, which is that important building block for all shell-forming organisms. But by 2100 and even earlier, those areas will be corrosive to those shells. And that means they'll start to dissolve, even if the animal is still living. Now, I'd like to show you, this is a pteropod, a planktonic snail, that's very common in both the northern and southern hemispheres in polar and subpolar waters. It's important food for salmon, pollock, and many other commercially important fish. And they have very, very thin shells, on the order of a few microns thick. So when we put a shell from Antarctica in seawater, with the same chemistry that is projected to occur by the end of this century, that's what happened. And what you're looking at right here, aggressively dissolved, but the calcium carbonate is all gone. What that is the organic matrix. Kind of like if you had a brick wall, it would be the cement between the bricks. The bricks would be the calcium carbonate crystals, and this is the matrix. So there's nothing left. The animal might, we have done experiments where we watch the animals, they would still be actively swimming, and their shells are dissolving. This is a summary slide. All other types of responses that we see in a variety of different organisms. Up at the top, these are the 4 different responses that you might get. If you put an animal in high CO2 or algae plant, you might get a decrease in some physiological response. It might increase, it might stay the same, or you might get this kind of optimal type curve. And what you'll see is that for calcification, the process of calcification, nearly all of the organisms show reduced calcification. And in the case of corals, it can be up to 60% reduced from normal seawater. The one winner, if you want to call a winner, a positive that increases, is photosynthesis for the seagrasses. Seagrasses are true plants, like on land, and they do better in high CO2. But many of them can be invasive. So just because a species does better does not mean your ecosystem is going to function better. So scientists in the United States and throughout the world now are very concerned about the impacts of high CO2 today and in the future on a variety of marine organisms. First of all, we're of course worried about the reduced calcification rates in both the plankton and bottom environments. We may also see shifts in algae, the very base of the food chain. And we could also see a reduced tolerance to other environmental stressors, like global warming. That in turn, we might see key changes to biogeochemical cycles, like nitrogen and carbon, changes to food webs also. We know enough right now to say we should reduce CO2 emissions. More studies are needed, though, to develop adaptive strategies for the future.
Thank you, Vicki. Thank you, Andrew. We're going to pause now in our presentation to take any questions that you have.